my first example is by using a two-tailed test in relation to a two-sided confidence interval. Now let's look at the other type. What if the testing is supposed to be a one-tailed test? Take note, if you use a one-tailed test and further use confidence interval, you cannot use a two-sided confidence interval anymore. What you need to construct instead is a one-sided confidence interval. Okay, so let us try a different scenario. So let's say we consider now a null hypothesis to be mu is greater than or equal to 5, and the alternative is mu is less than 5 with the given values in the study. And let's say the test was run and we concluded that we have to reject the HO, meaning to say this is no longer the true statement. That is, the mean should be less than 5. Again, by the hypothesis testing, we only know that the value is less than 5. But we don't know up to what value is, or what is the maximum possible value for the mu. If it is a number less than 5, so meaning to say it could be a number less than 5, up to what number can we accept the mean? Is it 4.99, 4.13, 4.01, 3.3? We don't know up to what number. Are we going to exclude some numbers very close to 5? So that is the goal now of the confidence interval. And with that, we can no longer use a two-sided confidence interval, but we will use a one-sided confidence interval. Now, as we can see, we are trying to look at the upper limit of that interval. How far can it go closer to 5? So, as we can see, an alternative hypothesis saying mu is less than 5 would create a confidence interval, a one-sided interval, having an upper limit u with a negative infinity on the right, on the left, because there is no boundary. Now to get the upper limit, we will use a very similar formula, and that is the mu must be less than the sample mean plus the z of an alpha. Now this is where the big difference that we can have in comparison with the two-sided confidence interval. In the two-sided confidence interval, we normally split the alpha into 2 because there is also another value that we have to find on the other side. Now, for the one-sided confidence interval, whether it's about the upper limit or the lower limit, the alpha is now concentrated on one side. So we no longer divide the alpha into 2. So I need you to be careful with this. If you are doing a one-tailed test and you decided to use a one-sided confidence interval, make sure to preserve the alpha that you are going to use in obtaining the upper limit or the lower limit. This is a big difference to the two-sided confidence interval. We no longer take the alpha or the half of the alpha when we use one-sided confidence interval. So to continue, so this formula will be, so z of alpha times, we have the standard deviation over the square root of n. So let us compute for the value. So this upper limit must be x bar, which is equal to 4.15 plus the z of alpha, the z of 0.05. Let's write that down first. And then the s to be 2.76 over the square root of 50. Now the z of 0.05 is equal to, this is 1.645. So if we compute for the value, so what we get is, so 4.15 plus 1.645 times 2.76 divided by the square root of 50. And just compute for this value using your calculator. And this value is equal to 4.7921. 4.7921. So the one-sided interval that we need is negative infinity up to 4.7921. And if we compare that to the decision of the hypothesis testing, that is, we rejected the null hypothesis, that is, the mu is greater than or equal to 5, because the interval even suggests that it can only be as high as 4.7921. Let me just pause here because I just want to emphasize that this is how you use the confidence interval if you are not going to use the hypothesis test to test a certain hypothesis. Now take note, in our null hypothesis, we said that the mu is greater than or equal to 5 and the h1 to be mu is less than 5. If we are not going to run a hypothesis test, but we constructed a one-sided confidence interval, one-sided because we need one side or one-tailed test supposedly, and this shows that the value for the mu can only be up to 4.7921. And clearly, when we say up to 4.7921, the value is less than 5. So it follows the alternative hypothesis. Therefore, with the confidence interval alone, we can already reject our null hypothesis even without running a hypothesis test. So that's one way to use the confidence interval aside from just estimating a certain value of a population. Now, if you want to use the confidence interval to really find the range of values that the mean can fall, or the possible values for the mean, then we can further, or we can still work on the lower limit of the interval. And that is, instead of using the plus sign, so we have the minus of z of alpha, because this is one side, 0.05 times s over the square root of n. And we will be using the same values, 4.15 minus 1.645 times s, which is 2.76 over the square root of 50. Note again that the alpha that I used to obtain this value is the alpha 0.05, and I'm not taking the half of alpha. So this value is equal to 3.5079. So this will be the lower limit if we are going to estimate the value of the mean. So this is 3.5079, while the upper limit is 4.7921. Again, we are now getting both of the values, the upper and the lower, because our goal now is to estimate. Here, we don't know, we know it should be up to 4.7921, but we don't know the smallest possible value. Okay, so this confidence interval will give us the estimate for the population mean mu. Now, if you take a look at what we have done, it seems that we have created a new relationship. Now, focus on the 0.05 and 0.05. In the earlier discussion of confidence intervals, these are the alpha over 2. So if the alpha over 2 is 0.05, then the alpha must be equal to 0.1. And for the confidence interval formula with an alpha of 0.1, we know that the confidence level is 90%, which gives us the idea that if the test is supposedly a one-tailed test, that uses an alpha of 5%, then to directly estimate the value of the mu, you can use a confidence interval with a confidence level of equal to 90%. And if you remember in the two-tailed test, we said that the alpha and the confidence level must total to 100%. But this is different because we are starting with a one-tailed test. In the two-tailed test, if the alpha is 5%, then the confidence level in the confidence interval must be 95%. That is because in the two-tailed test, the 5% was distributed to two sides, having 0.025 on one side and 0.025 on the other side. Now for the one-tailed, the effect of that is the value alpha is concentrated on one side. It could be alpha on the right, which is 0.05, or the alpha on the left, which is 0.05. And if we combine these two, what we create actually is a 90% confidence interval. Because the remaining value here, if we take away these two values, total of 10%, the remaining is 90%. Okay, so I hope that you were able to see that important relationship. That if you have one-tailed test supposedly to do, but you decided to use a confidence interval, you can go straight to using a 90% confidence interval to estimate the value for the mean in the given one-tailed test. Let us close this discussion by showing you one last example, and this time using an alternative hypothesis that is that of greater than. So let us consider the following given. Now it could be any study with the following information is about a proportion, and that the null hypothesis is the proportion is less than or equal to 0.60 or at most 60%. So the alternative hypothesis is the opposite, which is the proportion to be greater than 0.60. Suppose that in that study, the level of significance that we need to use in testing this hypothesis is 0.05, and when we gathered the data, we found that the sample proportion to be 0.625 from the sample size of 200, meaning to say we asked 200 respondents for this study. So let us show that without using a hypothesis test, let us use a confidence interval to test the hypothesis, and that is the mu, or the p rather, this is p. So we have the p, the proportion to be greater than 0.60. And then after that, let's create a confidence interval that contains the true population proportion, but in relation to the significance level set for the test. That is, the significance level set for the test is alpha equals 0.05. Now, before I even go to the solution, take note that the alternative hypothesis is a statement of inequality. Therefore, if we have to perform the hypothesis testing, we are supposed to perform a one-tailed test. So that means that when we create a confidence interval in testing the hypothesis, we should be using a one-sided confidence interval. Now, to know whether to find the upper limit or the lower limit, always focus on the alternative hypothesis. If the alternative hypothesis says that p is greater than or equal to 0.60, and that is what we want to find some evidence to support this claim, then our goal is to check, are we going to have a little more than 0.60 or a value that will cover 0.60. So as we can see from this analysis, that what we want is actually a lower limit and not an upper limit. Therefore, we have to get that one-sided confidence interval with lower limit L and an upper limit which is already with no boundary, so that is a positive infinity. The lower limit will be p hat minus the z of, now focus on this, you should not divide the alpha by 2 because this is a one-sided confidence interval. So z of alpha times the margin of error, which is p sub 0 q sub 0 over n. So using the values that we have, the p hat is, the sample proportion is 0.625. The z of alpha is the z of 0.05, and then the square root of p sub 0. The hypothesized proportion is 0.60. Therefore, the q sub 0 is 0.40 divided by the sample size n, which is 200. Now the z of 0.05, the z of 0.05 is equal to 1.645. So the computation becomes 0.625 minus 1.645 times the square root of 0.60 or 0.6 times 0.4 or 0.40 divided by 200. If we compute for this value, so we will get, so let's calculate, 0.625 minus 1.645 times the square root of the fraction 0.6 times 0.4 divided by 200. And the value is 0.5680 or 0.57. So take a look at what we have obtained. The lower limit of the one-sided confidence interval is 0.57, and this will go all the way to positive infinity. Note that the task was only to check, was only to test the hypothesis, and that is, so we have HO to be, the proportion is less than or equal to 0.60, and H1 is P greater than 0.60. If we place the numbers on the number line, you will clearly see, so take a look at this, 0.60, if this is 0.60, then 0.57 is somewhere here. Now, the confidence interval is allowing us to get numbers smaller than 0.60. So this claim that P is greater than 0.60 is not correct because the value can go lower than 0.60. With that, we say that we cannot reject, we do not reject HO because there are values that are less than 0.60. Do not reject HO. So this is how we use the confidence interval to test a hypothesis. So, but again, in the project, you are expected to show me that you can perform the hypothesis testing. So even if this is another way to test a hypothesis, I would like to see you perform hypothesis testing in the project. Okay? But just to show the relationship so that when you go and do your own research, you have different ways on how to test a hypothesis. So now for the second task, our second task is to create a confidence interval that contains the true population proportion in relation to the significance level set for the test, which is alpha is equal to 5% or 0.05. Now, so as we know, the proportion could go as low as or a number very close to 0.57, which these values are less than 0.60. But how large can the proportion be? Okay, so we are going to make an estimate of that. So this is now the second application of the confidence interval, and that is to create a range, okay, up to what values can we consider in relation to the testing of the hypothesis, which is alpha equals 5%. So we should already note that for the interval that we need, we have found the lower limit to be 0.57. So what's left for us is to find the upper limit. So it's basically doing the same thing, except that we have to use the plus sign instead of the minus sign to get the upper limit. So we have the sample proportion plus the z of alpha. We do not take the half of the alpha because this is the sign for a one-sided confidence interval that should be linked to the one-tailed test. Z of alpha times the square root of p sub 0 q sub 0 over n. So we have 0.625 plus z of 0.05. So this is z of 0.05, which is what we know as 1.645 times the square root of p sub 0, which is 0.6 times 0.4 divided by 200. And let's compute for the value. So 0.625 plus 1.645 times the square root of the quantity 0.6 times 0.4 over 200. This gives me 0.6819. So this is 20. So as we can see, the confidence interval that estimates the proportion is 0.57. Well, we can now cut this up to 0.68. Now, if you take a look at this confidence interval, now in the test we use a 5%. For the estimate, because this is using a one-tailed, we needed to preserve 5% on the other side and 5% also, or 5% on one side and 5% on the other side. So the confidence interval is actually based on a 90% confidence interval. Okay, so this is our estimate of the proportion that is directly related to the test of hypothesis using alpha equals 5%. So meaning to say, the proportion cannot be 70%. It cannot be 69% because it could only go as high as 68%. Okay, so to summarize what we have done in this second part of the lesson, we extended the concept of the relationship with the hypothesis testing to that of the confidence interval in the case of one-sided confidence intervals. And these one-sided confidence intervals are used when the test is supposed to be conducted using a one-tailed test. Now, you have to keep in mind that when you further get the confidence interval that is related to the hypothesis testing that is supposedly done, take note that there is no change in the alpha. We do not take the half of alpha in this case because otherwise it will not give us the appropriate value that corresponds to the significance level we set for the test. Okay, so I think that's all for this lesson. I hope you were able to understand the concepts that I presented here. Thank you.